Welcome to today's walkthrough of LeetCode problem number 536, construct binary tree from string. In this problem, we'll dive into reconstructing a binary tree from a specially formatted string representation. Stick around as we explore the problem details and its solution step by step. In this problem, you're given a string S that represents a binary tree, encoded in a specific way. The string includes integers, which can be positive or negative, to represent the values of the nodes. It also uses parentheses to define the structure of the tree. The first set of parentheses defines the left child of a node, if it exists, and the second set defines the right child, if it exists. Your goal is to reconstruct the binary tree from this string and return the root node of the tree. The input to the problem is a single string S, and the output is the root node, represented as a tree node object. Let's look at some examples to understand the problem better. In the first example, the input string is S equals 4, 2, 3, 1, 6, 5. The tree constructed from this string has 4 as the root node. The left subtree, represented by 2, 3, 1, shows that node 2 is the left child of the root, with 3 as its left child and 1 as its right child. The right subtree, represented by 6, 5, shows that node 6 is the right child of the root, with 5 as its left child and no right child. This gives us the complete tree structure shown here. In the second example, the input string is S equals 1, 2, 4, 3. The root of the tree is 1. The left subtree, defined by 2, 4, indicates that 2 is the left child of the root, with no left child of its own, but it has 4 as its right child. The right subtree, 3, shows that 3 is the right child of the root and does not have any children. This results in the tree structure shown here. In the third example, the input string is S equals -1, 2, 3, 4, 5. Here, the root node is -1. The left subtree, 2, represents a node 2 with no children. The right subtree, 3, 4, 5, represents a node 3 with 4 as its left child and 5 as its right child. This creates the tree structure shown here, with the root node -1 having both left and right subtrees. Now, let's outline some constraints and edge cases for this problem. The number of nodes in the tree can range from 1 to 10⁻⁴, and each node's value will be within the range of -10⁻⁵, 10 to the power of 5. The input string S is always valid, with no extra spaces, and the parentheses are well formed. For example, if the input is S equals 1, 2, the tree will have the root node 1 with no left child and 2 as the right child. Similarly, for S equals -10, 20, -30, the root will be -10, with 20 as the left child and -30 as the right child. These examples help clarify how the string format handles different tree structures, including cases with missing children or negative node values. To solve the problem of constructing a binary tree from a string, we start by understanding how the string encodes the tree structure. The string uses integers for node values and parentheses to represent relationships between parent and child nodes. One possible approach to tackle this is the brute force method, where we use recursion combined with manual parsing. The idea here is straightforward: we process the string character by character. First, we parse the numeric value for the root node. Then, using the parentheses as boundaries, we recursively parse the left and right subtrees. As each node is constructed, it is connected to its parent. While this approach is simple and aligns well with the structure of the problem, it can be inefficient. The main drawback is that slicing substrings repeatedly during recursion can add significant overhead, leading to a worst-case time complexity of n². For large strings, this inefficiency becomes a serious limitation. Despite its simplicity, this method is not ideal when performance matters. An optimized approach addresses the inefficiencies of the brute force method, particularly the issue of substring slicing, by using index tracking. Instead of creating new substrings during recursion, we maintain an index pointer that allows us to parse the string directly. This approach can be implemented either iteratively or recursively. By using a stack or managing indices explicitly, we can efficiently determine the boundaries of subtrees without redundant operations. The steps are as follows: traverse the string with an index pointer, parse numeric values to create nodes, and use a stack or recursion to track subtree boundaries based on parentheses. This approach processes the string in linear time, (n), as it avoids unnecessary substring operations. However, it does require careful management of indices and stack operations, which adds some complexity to the implementation. Overall, the optimized approach is both efficient and practical, making it a strong choice for solving the problem. Another alternative is a full stack-based parsing approach, which eliminates recursion entirely and relies solely on a stack to simulate the depth-first traversal of the tree. With this method, we traverse the string one character at a time. As we parse numeric values, we create nodes and push them onto the stack. Parentheses then serve as signals for when to pop nodes from the stack and attach them as children to the appropriate parent node. The traversal continues until the entire tree is constructed, with the root node being the last remaining node in the stack. This method is efficient, processing the string in O(n) time, and it avoids the recursion overhead completely. However, it comes with its own trade-offs. Managing stack operations adds a layer of complexity to the implementation, and while it is an effective solution, it may be less intuitive than the recursive approaches for some. Nonetheless, this method is a viable alternative for those who prefer iterative techniques over recursion. The chosen strategy for this problem is the optimized approach, recursive parsing with index tracking. This method strikes the best balance between simplicity and efficiency. By avoiding substring slicing, it eliminates the inefficiencies of the brute force method. At the same time, it maintains the elegance of recursion, which aligns naturally with the structure of the problem. The optimized approach is straightforward to implement and doesn't require additional data structures like the stack-based approach. One of the key insights here is the one-to-one mapping between the string's format and the tree's structure, which makes recursive parsing with index tracking both intuitive and efficient. By maintaining an index pointer throughout the parsing process, we reduce overhead and ensure that the solution is optimal in terms of time and memory usage. This approach effectively leverages the problem's constraints to deliver a clean and efficient solution. When comparing the chosen strategy to the alternatives, we see clear trade-offs. The stack-based approach avoids recursion but introduces complexity with managing stack operations. On the other hand, the brute force approach is easier to understand and implement but becomes highly inefficient for larger strings due to the overhead of slicing substrings. The chosen strategy achieves the best balance, combining the clarity of a recursive solution with the efficiency of index tracking. In terms of complexity, the time complexity is O(n), where n is the length of the string, as we process each character exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. This is optimal given the problem's constraints. Ultimately, the chosen approach stands out for its ability to handle the problem efficiently while remaining aligned with the natural structure of the input string. To construct a binary tree from the given string, we need to carefully parse its structure. The string uses integers to represent node values and parentheses to define parent-child relationships. Our first step is to parse the string. By iterating through it, we extract meaningful information such as node values and the positions of their children. We'll use an index pointer to navigate through the string. Next, we use a stack to track parent nodes. The stack allows us to maintain context as we process each node in the tree. The node at the top of the stack represents the current parent node. When we encounter an integer in the string, we parse it to get the node's value. This includes handling multi-digit numbers and negative values. Once the value is extracted, we create a new tree node instance, which represents a node in the binary tree. These steps form the foundation of our approach to reconstructing the tree structure. After creating a new node, the next step is to determine its relationship with the current parent node. If the stack is not empty, the new node is associated as either the left or right child of the node at the top of the stack, depending on the current structure defined in the string. To handle the tree structure, parentheses play a critical role. When we encounter an opening parenthesis, it indicates that we are about to process child nodes. At this point, we push the current node onto the stack to keep track of it as the parent. Conversely, when we encounter a closing parenthesis, it signals that we have finished processing the current subtree. We then pop the top node from the stack as we move back up the tree. Once the entire string has been traversed, the root node of the tree remains, which is the first node created and never popped. This root node is returned as the result of the function. Key insights include the importance of the stack for maintaining parent-child relationships, correctly parsing numbers even when they are multi-digit or negative, and recognizing parentheses as structural delimiters. It's essential to handle edge cases to ensure the algorithm works for all possible inputs. For instance, if the string is empty, we simply return none, as there is no tree to construct. If the input string represents a single node, such as 1, we return a tree with only the root node and no children. For more complex cases, like nested structures with missing children, we ensure that the tree is constructed accurately based on the string's format. Regarding data structures, the stack is indispensable for managing parent nodes during the tree's construction. It allows us to correctly associate child nodes with their immediate parents. The treenode class is another critical component, as it represents the nodes of our binary tree, storing the value and pointers to the left and right children. Key operations include string parsing, where we efficiently extract integers and process parentheses, treenode creation, as we dynamically construct nodes, and parent-child association, where the stack helps us link nodes correctly. By iterating through the string in linear time, O(n), we ensure the algorithm is efficient. The algorithm operates with a time complexity of O(n), where n is the length of the string. Each character in the string is processed exactly once, making the traversal efficient. The space complexity is O(h), where h is the height of the tree, as the stack requires space proportional to the depth of the tree being constructed. To better understand these concepts, let's walk through an example with the input string 4, 2, 3, 1, 6, 5. First, we parse 4 and create the root node. Upon encountering an open parenthesis, we push 4 onto the stack. Then, we parse 2, create a node, and set it as the left child of 4. Another open parenthesis signals that we push 2 onto the stack. Parsing 3, we create a node and set it as the left child of 2. A closing parenthesis indicates that we pop 2 from the stack. Next, parsing 1, we create a node and set it as the right child of 2. Another closing parenthesis means we pop 4 from the stack. Parsing 6, we create a node and set it as the right child of 4. Finally, parsing 5, we create a node and set it as the left child of 6. The final tree structure resulting from the example input string 4, 2, 3, 1, 6, 5 looks like this. The root node is 4, with 2 as its left child and 6 as its right child. Node 2 has 2 children, 3 as its left child and 1 as its right child. Node 6 has only 1 child, 5, as its left child. This tree is a clear representation of the encoded string and demonstrates the algorithm's ability to correctly reconstruct the binary tree from the input. Here, we begin by defining a treenode class to represent each node in the binary tree. Each treenode has 3 properties: val for the value of the node, and left and right to reference its left and right child nodes, respectively. Next, we define the main solution class, which contains the str2tree method. This method will take a string input s and construct the corresponding binary tree. To start, we define a helper function, parse_number, which is responsible for extracting a numerical value from the string. It checks if the current character is a negative sign, processes the digits one by one, and returns both the parsed number and the updated index. This ensures that we can correctly retrieve each node's value when constructing the tree. Additionally, we define the construct_tree function, a recursive helper that will build the tree structure. It begins by checking if the current index has surpassed the string's length, in which case it returns none, indicating no more nodes to process. Now, within the construct_tree function, we start by parsing the root node's value using the parse_number helper, which gives us the value and the updated index. We then create a new tree node with this value. Next, we check if the current character at the index is an opening parenthesis. This indicates the presence of a left child. If so, we recursively call construct_tree, advancing the index to process the left subtree. Similarly, if another opening parenthesis is encountered, it signals the presence of a right child, and we recursively construct the right subtree. Once the child nodes are processed, we look for a closing parenthesis, and increment the index to skip past it. Finally, when the entire tree is constructed, the root node and the remaining index are returned. If the input string is empty, we simply return none, indicating no tree to construct. Otherwise, we call construct_tree starting at index 0, and the completed tree is returned as the result. Here, we start by defining the structure of a binary tree node using the treeNode class. Each node contains an integer value and references to its left and right child nodes. The constructor initializes the node with a given value. Next, in the solution class, we define the method str2tree, which takes a string representation of the binary tree as input and returns the root of the constructed tree. If the input string is null or empty, we simply return null, as there is no tree to construct. To help with the recursive parsing of the string, we use an integer array, index, to keep track of our current position as we traverse the string. The method then calls constructTree, which is the recursive function responsible for building the tree structure from the string. The constructTree method begins by checking if the current index has reached the end of the string. If it has, we return null, indicating no further nodes to process. To parse the value of the current node, we first determine the starting position of the number. If the character at the current position is a negative sign, we increment the index to include it as part of the number. Then, we continue advancing the index until we encounter a non-digit character, capturing the entire numeric value. This value is converted into an integer and used to create a new treeNode instance, which will serve as the root of the current subtree. After parsing the root value, we check if the next character is an opening parenthesis, indicating the presence of a left child. If so, we increment the index to skip the parenthesis, recursively call constructTree to build the left subtree, and then increment the index again to skip the closing parenthesis. If another opening parenthesis is found after processing the left child, it indicates the presence of a right child. We increment the index to skip the parenthesis and call constructTree recursively to construct the right subtree. Once the right subtree is built, we increment the index to skip the closing parenthesis. At this point, both the left and right subtrees, if present, have been attached to the current root node. Finally, the method returns the root node, which now represents the fully constructed subtree for the current section of the string. This process continues recursively until the entire string has been processed and the binary tree is fully constructed. To solve this problem, we start with the input string 4, 2, 3, 1, 6, 5. The first step is to call the str2tree function with this string. Inside, the construct_tree function is responsible for building the tree. At the beginning, the index is at 0, and we parse the number 4, which is the root node. After parsing, a tree node is created with the value 4, and the index moves to 1. Next, at index 1, we encounter a left parenthesis, which signals the start of the left subtree. To process this, we call construct_tree recursively with the updated index at 2. Here, the number 2 is parsed, and a tree node is created with the value 2. Moving forward, another left parenthesis at index 3 indicates that this node has a left child. We make another recursive call, where the number 3 is parsed at index 4. A tree node is created for this value, and since the closing parenthesis is encountered right after, the subtree rooted at this node is complete, and we return tree node 3 with the updated index of 6. Similarly, at index 6, another parenthesis indicates the right child of node 2. The number 1 is parsed, a tree node is created for it, and the subtree is finalized when the closing parenthesis is found. This gives us tree node 1 with the updated index of 9. At this stage, node 2 has both its left and right children constructed. With the left subtree complete, we now focus on constructing the right subtree of the root node. Starting at index 9, we encounter a left parenthesis, which signals a new child. We call construct_tree recursively with index 10. The number 6 is parsed, and a tree node with the value 6 is created. Moving to index 11, another left parenthesis indicates a left child for node 6. Making a recursive call again, the number 5 is extracted at index 12, and a tree node is created for it. Once the closing parenthesis is found, the subtree for this node is finalized, and the function returns tree node 5 with index 14. At this point, node 6 has its left child constructed, and since no further children are indicated, the right subtree of the root node is now complete. The function then returns the root node, tree node 4, with the full tree constructed. The final tree has node 4 as the root, with node 2 as its left child and node 6 as its right child. Node 2 itself has children 3 and 1, while node 6 has child 5. The tree structure is visually represented as shown, with the root correctly connected to its respective children. Now consider a different input, 1, 2, 3, 4. Here, the root node is parsed first, which gives the value 1 at index 0. A tree node is created with this value. The left parenthesis at index 1 indicates a left subtree, so we move forward and parse the number 2 at index 2. A new tree node is created for this value, and once again, a left parenthesis at index 3 signals that this node has a left child. Parsing the number 3 at index 4 results in another tree node being created. As the closing parenthesis follows immediately, this subtree is wrapped up, forming a chain where node 2 has node 3 as its left child. The partial tree now consists of node 1 as the root, with node 2 as its left child and node 3 as the left child of node 2. Next, we process the right subtree, where the number 4 is parsed at index 9. A new tree node is created for this value, making it the right child of the root node. With no further children, the final tree is complete. The root node 1 has node 2 as its left child and node 4 as its right child, while node 2 itself has node 3 as its left child. The structure is now fully constructed and visually represented. Finally, let's look at the input -1, 2, -3. The root node is parsed first, and the number -1 is extracted at index 0. A tree node is created with this value. The left parenthesis at index 2 indicates a left subtree, so we parse the number 2 at index 3. A new tree node is created for this value, and it is added as the left child of the root node. Moving forward, another parenthesis at index 5 signals a right subtree. The number -3 is parsed at index 6, and a tree node is created for this value. This node becomes the right child of the root node. With no further children indicated, the tree construction is complete. The final tree has -1 as the root, with 2 as its left child and -3 as its right child. This structure is visually represented, showing a balanced arrangement where the root has both left and right children properly connected. The time complexity of this function primarily depends on 3 components: parsing the input string, constructing the binary tree recursively, and matching parentheses. First, parsing numbers involves iterating over consecutive digits to extract integer values, which means that each character in the string is processed exactly once, contributing O(n) to the time complexity. Next, the recursive tree construction ensures that each node in the binary tree is processed exactly once as well. While the recursion depth depends on the height of the tree, each recursive call only operates on a specific segment of the string, so this also contributes O(n). Finally, the matching of parentheses is handled in constant time for each character, as every opening parenthesis corresponds to a closing one. When we combine all these factors, the overall time complexity is O(n), as every character in the string is processed a constant number of times. Now, let's consider the space complexity, which depends on 2 main factors: the recursion stack and the memory used to store the binary tree. The recursion stack depth corresponds to the height of the binary tree. In the worst-case scenario, where the tree is highly unbalanced, this depth could be O(n). In the best-case scenario, with a perfectly balanced tree, the depth is reduced to O log n. Additionally, we need to account for the memory required to store the tree nodes. Since each node in the binary tree corresponds to an element in the string, and the string has n characters, this contributes O(n) to the space complexity. Combining these 2 factors, the overall space complexity is O(n) in the worst case, with the recursion stack being the dominant factor in unbalanced trees. When analyzing the best, average, and worst cases, we see that the time complexity remains consistently O(n) across all scenarios, as every character in the string must be processed exactly once. For space complexity, the best case occurs when the tree is balanced, minimizing the recursion depth to O log n, while the worst case happens with a highly unbalanced tree, where the recursion depth grows to O(n). In the average case, the recursion depth lies somewhere in between, and the space complexity is still close to O(n). What makes this solution efficient is its linear time and space complexity, compared to a naive approach that might revisit parts of the string multiple times, leading to a quadratic time complexity of O(n squared). By parsing the string in a single pass and constructing the tree recursively, we avoid redundant computations and achieve a much faster and more memory-efficient solution. Finally, the mathematical proof for the big O complexities reinforces why this solution is optimal. Each character in the string is processed a constant number of times during parsing, ensuring time complexity is proportional to the length of the string, or O(n). The recursion stack's growth depends on the tree height, which is O(n), in the worst case an O log n, for a balanced tree. Tree node storage also contributes O(n), as each node corresponds to a parsed value. When combining these factors, both time and space complexities are dominated by O(n), making the solution highly efficient. This linear performance guarantees that the approach scales well even for large inputs, solidifying its efficiency and practicality. When solving this problem, there are a few common mistakes to watch out for. First, incorrectly parsing parentheses can result in assigning subtrees to the wrong parent. This often happens because cases where a node has only one child or no children are overlooked. A good way to avoid this is by using a stack or recursive parsing to handle the nested structure of the parentheses properly. Next, make sure to handle negative node values. A frequent mistake is assuming all integers in the string are positive, which breaks the logic when encountering a dash character. The solution here is to explicitly check for negative signs and adjust the parsing accordingly. Another pitfall is inefficient string manipulation. Using string slicing excessively during recursion can lead to O(n) squared complexity since slicing creates new substrings. Instead, tracking the current position with indices is much more efficient. Finally, don't assume the input is always valid. Unmatched parentheses or invalid characters can cause unexpected errors, so it's important to add checks for these scenarios to ensure robustness. Additionally, overlooking edge cases is a common source of bugs in this problem. Examples include handling empty strings, single-node trees, or deeply nested trees. This often occurs when developers focus on the general case and neglect these special scenarios. The solution is to test your implementation thoroughly against a variety of edge cases early in the process. Now, from an interview perspective, this problem serves as a classic test of your ability to use recursion for tree construction while managing state effectively. Interviewers often look for your ability to recognize patterns in recursive parsing and your focus on optimizing the solution. For instance, reducing overhead by using pointers instead of slicing can demonstrate an optimization mindset. You should also be prepared to discuss how your solution handles edge cases and explain connections to related tree concepts, such as traversal, serialization, or deserialization. To deepen your understanding of related problems, here are some excellent ones to explore. Problem 105 involves constructing a binary tree from pre-order and innerorder traversal, while Problem 106 covers construction from innerorder and post-order traversal. Both require a strong grasp of parsing and tree-building logic. Problem 297 focuses on serialization and deserialization of a binary tree, which is highly relevant since the string-to-tree transformation in this problem is essentially a form of deserialization. Lastly, Problem 889 challenges you to construct a binary tree from pre-order and post-order traversal, adding another layer of complexity to tree reconstruction techniques. These problems share common themes with this one, so practicing them can help reinforce key concepts and strategies. Now, let's consider some alternative approaches for solving this problem. One common method is recursive parsing. Here, a helper function is used to recursively parse the string, creating nodes and subtrees along the way. This approach is intuitive and aligns well with the recursive nature of tree structures, but it may involve additional overhead if string slicing is used. Another option is stack-based iterative parsing. By using a stack to maintain the nodes and their parents during the parsing process, you can avoid recursion, which helps reduce the risk of stack overflow for deeply nested trees. However, this approach demands careful state management and can be more complex to implement. Finally, the two-pointer technique can optimize time complexity by avoiding string slicing altogether. Instead, you use pointers to track positions within the string. While this method is efficient, it does require meticulous pointer management, which can make debugging slightly more challenging. Each of these approaches has its own trade-offs, so the choice depends on the specific constraints and priorities of the problem you're solving. Great job on completing this walkthrough. In summary, we tackled the problem by leveraging recursive parsing to reconstruct the binary tree. Remember to practice similar problems to build a strong foundation in recursion and tree manipulation. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!